Electromagnetic plunger. Electromagnetic plunger works on AC current and consists of the coil and a movable part, plunger. Plunger position is controlled by the external spring. Coil has 500 turns with the current 1 ampere. AC frequency is 50 Hz. Plunger is made of steel with relative magnetic permeability of 1000. Our task is to estimate the plunger displacement at the given current value. The plunger has cylindrical shape and the coil is cylindrical. We can simulate this in two-dimensional axisymmetric model. First, I plan to run AC magnetic analysis to compute magnetic force. Then I will simulate mechanical problem to compute the plunger displacement. I will use the problem coupling to automatically transfer forces from magnetic problem to mechanical problem. Okay, let's start QuickField now. In QuickField I create new problem. Problem name plunger. Next. Problem type is AC magnetics. Frequency is 50 Hz. Model class is axisymmetric. Length units are millimeters. Finish. On the left you can see the problem pane and on the right you can see the geometry model editor window. You can draw the geometry model here or you can import the geometry model from the AutoCAD DXF file. Geometry is simple, so I will draw it here right now. In axisymmetric problems, the axis of the rotation is a horizontal one, and we should draw only the upper half of the cross-section. Switch to insert mode, click and drag to draw the line along the horizontal axis. Then follow to the edit, insert shape, rectangle. The plunger length is 70 millimeters and the plunger radius is 7 millimeters, and this will be the anchor point. Insert. Now insert another rectangle representing the coil cross-section. Coil thickness is 12 millimeters, coil length is 50 millimeters, and the coil inner radius is 8 millimeters. Insert. Close. Zoom to fit. Let's zoom in. Here you can see the plunger and the coil. And the plunger is extended from the coil for 7 millimeters. Switch to select objects mode. Select the plunger. Right click. Move selection. Displacement to the right for 7 millimeters. Okay. The magnetic field is distributed not only inside the coil and the plunger, but also in the air outside. QuickField cannot calculate magnetic field distribution in the infinitely large space, so we need to restrict the simulation domain. Switch to insert mode. Zoom to fit, change the line type to be the half arc, and draw the air block boundary. Now let's assign labels. For labels we will provide physical properties. Switch to select objects mode, click the object to select, and type in the label. This is the air. Let's zoom in. Switch the zooming mode off, click to select, this is coil, click to select, this is plunger. Okay. Double click the label in the tree. The relative magnetic permeability of the air is 1. Okay. Relative magnetic permeability of the plunger is 1000. Okay. And relative magnetic permeability of the copper is 1. and I will specify the total current value, which is 500 ampere turns. Okay. That is all for block labels, but we should also assign labels to the boundaries. QuickField automatically assigns proper boundary condition to the axis of the rotation, and far away from the plunger the magnetic field fades to 0. So I will click to select and assign label external boundary to this edge, and for this edge I specify 0 magnetic potential. Okay. Before I start the analysis, I should build the finite element mesh. Just click this button and the mesh will be constructed. Then save all problem files and you can run the analysis. The problem has been solved. Let's take a look at the results. Here you can see the magnetic field lines and the current density distribution. You can adjust the field picture and switch on, for example, the flux density distribution. The correspondence between the colors and the numbers you can see in the legend. And you can get exact value in any point if you use the local values tool. Just click any point and here you will get the flux density, field strength, current density, if any, and other parameters. You can edit the point coordinates here, and you can use contour tool to construct XY plot. For example, I will select the axis, just click the edge, click another edge, and click another edge, and switch on the XY plot. This is the flux density distribution along the solenoid axis. And the exact numbers you can see in the table. Coordinates, flux density, field strength, and other parameters. You can also use contours to calculate integrals. Contour clear, click to select the plunger, follow to the integrals, Maxwell force. Here is the force acting on the plunger. So we have come to the next task, calculation of the mechanical displacement of the plunger. QuickField allows to simulate multi-physics problems, and I would like to pass magnetic force distribution from AC magnetic analysis to the stress analysis. That is done through the problem linking. But first I should create the stress analysis problem. Back to QuickField, create new problem. Problem name is plunger stress. Next, problem type is stress analysis. Model class is axisymmetric. Length units are millimeters. To be able to pass data from one problem to another, both problems should be based on the same geometry model file. So I click Browse button here and search for the model file that was used in AC magnetic analysis, which is plunger.mod. Here it is. Open, finish. So the geometry model is the same and we already have labels assigned, but now we should provide mechanical properties to the labels. We do not calculate stress in the air, so for the air I don't specify any values. Just open the dialog and click OK. Now instead of the question mark you can see the exclamation mark. This mark indicates that this label is not an unknown label. It is a label with empty dataset, and this label is excluded from the simulation analysis intentionally. Well, and also I'm not interested in the stress in the coil. So for the coil I do not specify any data. For the plunger, which is made of steel, the Young modulus is 200 gigapascals and the Poisson ratio is 0.3. Okay. The external boundary has no physical meaning in stress analysis problem. Again, I open the label properties dialog and do not specify any values. Just click OK. Now let's add the spring. The spring is connected here at this vertex. So I switch to select objects mode, select this vertex and assign the label spring. The spring rigidity coefficient is 50 newtons per meter. Okay. We have finished with the material properties. Now let's set up the link. Open the problem properties, follow to the links tab, choose the data type magnetic forces, browse for the problem file, which is plunger.pbm. Here it is, open and add the link. Okay. Now the link is added to the tree and we can start the analysis and get the error message. The linked problem results are out of date. Indeed, we have modified the geometry model. We assigned new label to this vertex and we have specified properties to this vertex in the mechanical problem. But there is no properties assigned to this vertex in the magnetic problem. Well, this vertex has no physical meaning in the magnetic problem. I do not provide any values to this label. Just open the dialog and click OK. And here you see the 0 mark next to the label name. Anyway, the problem setup has changed and we should run the magnetic analysis again. Solve magnetic problem, save all simulation files. No need to look at the results now, and I can proceed with the stress analysis. Solve, save all modified files. No more error message this time, and I can take a look at the results. You can see the deformed shape of the plunger. In fact, it is scaled many times. If you open the field picture properties and switch on the displacement color map, you will see that the displacement of the plunger is only 0.78 millimeters. And that is all I need to know here. Of course, you can use the local values tool. Click any point and get the exact value of the displacement, or you can use the contour tool to construct XY plots or calculate integrals. For example, I select the plunger and I can calculate the force. Here you can see that beside the horizontal force acting on the plunger that you have already calculated in AC magnetics, there is a radial force trying to tear the plunger apart. If you search for the electromagnetic plunger on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.